Alright, so Sam and I completed an experiment on Muon Decay time, and so to introduce this topic, uh, electromagnetic radiation comes from outside of the Earth's atmosphere and interacts with the particles at the upper atmosphere, the air particles there, and a muon is comes from this reaction is shot really, really fast towards the Earth, almost the speed of light. Now, muons are expected to decay within 2.2 microseconds. This comes from literature values cited later in the paper. Doing a little calculation, they're only without the effect of time dilation, they're expected to disappear within zero point 0.5 kilometers. Now, under the effect of time dilation, it becomes apparent that that distance is way greater. And we can actually, that's why we detect the muons at the Earth's surface. So there's a lot of math on this slide, but what we need to understand is the relation between the number of muons and the initial number of muons is equal to this negative exponential decay, and it's solely a function of time, elapsed time, right? There's no dependence on reference frame. And this allows us to measure the decay time, this constant within lambda, the mean decay time for a lifetime uh, uh, of a muon at rest, right? And but it allows us to measure it from Earth, not from the muon's reference frame, which is pretty cool. So we did this by fitting different collecting the bin sizes of different permutations ranging from 0.5 microseconds to 2 microseconds, and then also bin width error of 10%, 20%, and 30%. And then we fit this negative exponential decay. Now, our experimental goals were to get the best fit for that exponential and extract the time of decay from it, and also using that to derive the charge ratio and confirm the Fermi coupling constant as well. These are our experimental results over here. Agree very nicely with literature values, and then yeah, these are the charge ratio literature values, and as you can see, 0.5 is like right in here. I'll talk about that later. Basically, in experimental methods, we used an apparatus that looks exactly like this. The muon comes in upon entry. It interacts with the flora in the scintillator via Coulomb forces, and the electrons go to this lesser energy state, right? And light is then emitted, and that flash of light goes to the photomultiplier right here, sends a voltage around. If the voltage is characteristic of a muon, then the discriminator sends a pulse out to the FPGA timer, and that's time 1. And then upon decay, another flash of light is emitted due to the interactions here. Photomultiplier sends another current. The discriminator does the same thing as it did before, and time 2 is measured. The time difference, if it's below 40 microseconds, will be considered. If it's above that, then it says, okay, this is not a muon decay, etc. We're doing mostly calibration in some of our experimental methods, making sure that the threshold on the discriminator was good and it allowed the muons to properly be detected. And I found this figure pretty useful, where when the threshold, say, is through C to H, the threshold on a discriminator, the time difference in the pulse is actually quite large if we consider the time difference on the x-axis. And then, say, if the voltage threshold were higher, then the time difference were less. And this is what we use to calibrate the discriminator, to make sure those waves characteristic of a muon were transferred to the FPGA timer. yeah, so after running the experiment for 48 hours, we did a little analysis and we used the 9 permutations of bin size and error. This was one of our plots just of the raw data in histogram form, and then our task was to fit it. So upon fitting, this is our best fit with a chi-square value of 1.04. You'll see this on the next slide. And now we're fitting with that relation where f of t is n, and n is n0 before. And then there's this beta term, which accounts for background radiation, and it's a vertical shift up. Clearly, on this, these are our results, right? So these are bin sizes, bin errors. We have our 9 possible permutations, and our best permutation is right here with bin size of 1 microsecond, 10% bin width error. Our decay time was 2.10 plus or minus 0.06 microseconds. And there was some background radiation that we were able to filter out. And our reduced chi-square fit was 1.04. So that's a really good fit. Going back to this, some of our points aren't in within like a standard deviation of the point, so that's a good fit. But moving on to the Fermi decay constant, we obtained that the Fermi decay constant was 1.20 times 10 to the negative fifth, plus or minus 0.06 times 10 to the negative fifth giga-electron volts. And our charge constant we obtained through some error propagation and using our new muon decay time was 1.55 plus or minus 0.02. And that just indicates that there are more positively charged muons than negatively charged muons, because negatively charged muons interact with the protons in the scintillator. So upon analysis, our results agree very well with literature values. Our median momentum was calculated to be somewhere in between 120 and 240 giga-electron volts over C, and there were low standard deviation errors upon all of our results. So that was nice. This is an example of a poor fit with a bad chi-square value. Error bars extend really far, so this is an overfit, reduced chi-square value, that is. And then this discusses background radiation. It's systematic, so it's good that we included this term to take out some of the background radiation. Now, in conclusion, these were the values measured where the time of decay was 2.1 microseconds approximately, and yeah.